Imagine you are training a brilliant student to identify different types of animals. You want them to be accurate, not just on the examples you show them, but also on new animals they have never seen before. What if your student consistently misidentifies certain animals or becomes completely confused by slight variations? This challenge lies at the heart of model performance in machine learning, and it is precisely why understanding and reducing both bias and variance is so crucial. Reducing bias and variance is important because it directly impacts a machine learning model's ability to generalize well to new, unseen data, which is the ultimate goal of nearly every predictive model. A model that effectively balances these two error sources will deliver accurate and reliable predictions, making it truly useful in real-world applications. Now, let us delve into why these two concepts are so significant. Bias represents the simplifying assumptions made by a model to make the target function easier to learn. High bias can cause a model to miss the relevant relations between features and target outputs, leading to underfitting. This is like our student consistently ignoring key features of certain animals, making broad generalizations that are often incorrect. On the other hand, variance refers to the model's sensitivity to small fluctuations in the training data. A model with high variance might learn the training data too well, capturing noise and specific details rather than the underlying pattern. This results in overfitting, where the model performs excellently on the training set but poorly on new data. Our student in this case might memorize every detail of the example animals, including a specific scratch on one, and then fail to recognize a perfectly healthy animal of the same species. The challenge is that bias and variance are inversely related, creating what is known as the bias-variance tradeoff. Efforts to reduce bias often increase variance, and vice versa. For instance, making a model more complex, such as using a deeper neural network or a higher-degree polynomial regression, can reduce bias by allowing it to capture more intricate patterns. However, this increased complexity also makes the model more sensitive to the training data, thereby increasing its variance. Conversely, simplifying a model to reduce variance might lead to an increase in bias, as it can no longer capture the true complexity of the underlying relationship. Mastering this balance is key to creating robust machine learning solutions. Techniques like regularization, cross-validation, and ensemble methods like bagging and boosting are specifically designed to navigate this trade-off. For example, regularization adds a penalty for complexity, helping to prevent overfitting and thus manage variance, while still allowing the model to learn meaningful patterns. Ensemble methods combine predictions from multiple models to reduce either bias or variance depending on their specific approach. For instance, bagging reduces variance by averaging the predictions of many independently trained models, while boosting focuses on sequentially training models to correct the errors of their predecessors, thereby reducing bias. Ultimately, the pursuit of reducing both bias and variance is about building models that are not just theoretically sound but also practically effective. By diligently addressing these two error sources, we can develop models that learn accurate representations from data, generalize reliably to new situations, and provide trustworthy predictions across diverse and dynamic environments. This ensures our machine learning systems deliver consistent and valuable insights, making them powerful tools for innovation and problem solving.